Hello, my name is Lynn Wallace. I'm a computer scientist, software engineer, systems engineer, and certified secure software lifecycle professional. And this is Thinking About Security as a Software Developer. If you ever worked for a large enough organization, you've gotten some training on what to do or not do to keep the network safe. Or maybe you've learned through other sources how to keep your sensitive data safe on the internet. That kind of training is great for network users, but it stops just short of being useful to us as coders, as the people who together write all the code that handles all the user's data. That training is like going to a national park and turning around after the visitor center. Unimaginable wonders lie just around the corner, but we don't go there. Very few programming schools require security lessons. But if you're smart enough to write non-trivial software, you're ready to learn this stuff. Now, this is not the usual secure coding training. While that is also essential for a software developer in today's world, it doesn't cover the design and architectural thinking that we do before and while we write code. 19 of the top 25 weaknesses occur prior to coding. Over the last 45 years, I've written a lot of software, some of it cool, some of it mundane. The surrounding pictures represent major parts of my career. I rarely thought about security while I did it, because like you, I wasn't taught to. Well, I thought a lot about software security recently, and knowing programming and programmers like I do, I belatedly realized that we programmers have our very smart and hardworking cybersecurity colleagues by the neck. Sorry, by the neck. If we don't think about security, they are ultimately doomed to failure in their efforts to protect our users' organization's IT from attack. As I'm talking, I invite you to try to think about any software that has no security considerations. I've thought about it for a few years, and I'll have my answer at the end. Pondering this question as we go through this material and beyond, you'll need to apply these basic concepts of cybersecurity to your hypothetical situation. You'll ultimately realize a few things. First, for the most part, security isn't hard to understand, and we know designing it in is many times easier and much less costly than trying to strap it on later. Second, this thinking will improve the security of all the code you write from now on. And third, as the designer and creator of the software, this is thinking that only you can do. The rest of this briefing consists of a mock pop quiz that clarifies our role in cybersecurity, followed by a slightly deeper dive into each of the cyber concepts and what they mean to us. Then we'll use the Wayback Machine to go to the very beginning of cyber and application security and discover some wisdom of the ages. Finally, I'll leave you with a little assignment. I know. You weren't expecting a test. But bear with me, this is just a 4-question thought exercise. If you create a vulnerability in the code, who did it? I'll define vulnerability later, but you don't need to know to answer this question, right? I didn't create the vulnerability. Your colleagues didn't. Your boss didn't. You created your vulnerability. Question 2. Who should fix it? You created the code. You know the code. You should fix it. Question 3. Who else can fix it? I'll give you a second to think about it. Of the other 8.5 billion people on the planet, your colleagues are the most capable of fixing your code. If you've moved on, whoever's assigned to maintain the code can fix it. Now we're getting to the point. Who can't fix it? I'm looking for a specific answer. With few exceptions, all the cyber team can do to protect the network from your vulnerability is to keep the wrong people from using your software. Maybe you were lucky or proactive and provided a configuration setting that can mitigate the risk. But usually, they must keep anyone from using your broken software. That means that all that wonderful functionality that you worked so hard to provide is unavailable. Your customer or user gets no value from your code. You failed. Hopefully, I've given you a bit of an epiphany. Now that you've started thinking about security, these lessons can stick with you for the rest of your career. While security is hard to get right in practice, you are smart enough to understand and think about it. We need to think about security while we're writing code because we make design decisions all day, every day. Without a sensitivity for security, we might not even think about how valuable our data is and unknowingly code a backdoor through all the security controls our users have in place. We might send that data to the wrong framework, the wrong server, the wrong service, the wrong log message. Again, this is thinking that only we can do. Here are the concepts I'm going to talk about. The definitions are mine thinking as a programmer. For the CIA triad over there on the left, we mainly implement the cyber requirements handed to us. But if those requirements happen to be missing, we need to dig into why, once we've learned how to look for them. The concepts in the middle are the ways we work with cybersecurity personnel to implement the CIA. On the right, we see where we programmers create security problems and ways we can avoid them and help limit the trouble caused by the inevitable issues that escape. The fact is, we actually use many of these security concepts all the time when developing software, but it's usually not to provide security. You've heard of encapsulation, static variables, private, protected, and public members. Those are all ways of keeping the data from where it shouldn't be so our code works and is cleaner. But controlling where the data goes also happens to be the root of cybersecurity. Applying those make it work concepts to also add security to the system is the part we're all missing. Confidentiality means controlling access to valuable information. Before we just roll right into controlling access, let's talk about valuable because it drives security. Value is subjective. Your customer or user needs to understand what their most valuable information is. A surprising amount of users don't give any thought to the question. If they don't tell you what's most valuable, ask them. Very large organizations make it easy to identify what's sensitive or valuable through classification and give us requirements for how to protect it. Of course, if you can't talk to your users, then it's on you to provide sufficient security in your code. To the user's valuable data, we need to add the data that we deal with or synthesize. It can be very valuable to an attacker. For example, if your code crashes and blasts a stack dump to the user's console, you may be handing an attacker the keys to your kingdom. They'll scrub all that information against the exploits they already have on hand and launch a potentially successful attack against a vulnerable part of your tech stack. Just as only some of your code has a need to access some of the data, only authenticated and authorized users who may not be human get to see confidential data. Otherwise, the data is encrypted at rest or in transit with a secure protocol. Run away fast from any programmer who says they wrote their own encryption. Encryption is extremely hard to get right. We are usually told which encryption implementations we must use, and in most cases, we should use trusted services to perform not only encryption, but most of the security functions, instead of writing it on our own. The most effective way for your software to protect confidential information is to minimize the amount of it you process. If your code can do its job without some sensitive data, don't keep it. Avoid extraneous copies of valuable data, keep the code that processes it well encapsulated, and overwrite the data after use. We need to protect sensitive data from unauthorized alteration to ensure that it is authentic and correct. Integrity contributes to a system's stability and reliability as well as the authenticity of data. I used to think that cybersecurity cares just whether the system is secure, not so much that it works. But incorrect information is incorrect if we produced it or if an attacker modified it. The cases during the Cold War when we almost blew ourselves up typically occurred when the system provided incorrect information about an impending attack and the user wisely decided to ignore it. Remember integrity when you're trying to answer my challenge to think of software that has no security considerations. Beyond the security benefit of digital signatures that signal to us whether data may have been tampered with, we also use hashes and checksums to perform error detection and correction in a quality system. Blockchain is immutable, which provides integrity, but it also makes correcting errors more difficult. And finally, if the data is encrypted, it's impossible for an attacker to covertly and transparently tamper with it. Availability is a concept that you should already be familiar with. It's about working code. Incidentally, I remember searching in the 80s and 90s for tips for writing secure code, and the advice at the time was, don't crash. Enter error handling, which I will gently emphasize later. You may well not have any requirements that say don't ever crash. And yes, I've worked with programmers who say, well, not crashing wasn't a requirement. So there's a long list of techniques we devised and you should already be familiar with to make sure our software keeps running. Dead or unreachable code should not be available because it is hidden functionality that could be used in an attack. Therefore, secure coding standards usually mandate its removal. Regarding redundancy, there is nuance. Scaling with the same software does provide availability for a distributed system. But if all copies fail the same way, it doesn't help in off-nominal situations like an attack. In very high assurance situations affecting safety, life, or the bottom line, the next critical, unreversible step may require a voting arrangement with non-identical paths. Authentication is making sure that the user is who they claim to be. Remember, a user is equivalent to a non-human caller of your function. You'll need a database of some kind with a schema, but it's typically not a relational database. Technically, LDAP, Lightweight Directory Access Protocol, is a protocol, but the acronym is used interchangeably with the user directory itself. An LDAP directory typically uses a tree structure of some kind. Microsoft uses a proprietary database for their Active Directory, which uses LDAP in its interface. Your user directory matches a list of all users with their authentication information. We should know that multi-factor authentication is something you know, something you have, and something you are. The something you are part usually requires special hardware such as fingerprint scanners or facial recognition. Think device drivers, bits and registers, other embedded system features. Because of all the compromises over the decades, we're beginning to add behavior and location to the factors. If I live in America, but log into the system from Shanghai, or if I log in at 3 a.m., that's a red flag. I always try to put least in front of privilege whenever I think or speak about it, and you should too. Your user directory should enumerate all the resources in the enterprise and all the users, and have a way, typically an ACL, of linking them with various levels of authorization to do CRUD, create, read, update, and delete. That's a lot of resources and a lot of users, so an administrative GUI is a way of making the granting and checking of authorization manageable. Of course, the ability to change the user directory itself, a user's authorization to other resources, is a crucial piece of authorization. Thus, your user directory needs to be under tight control. And by the way, use the automated workflows in the list. Whenever I hear automated, automatic, or automation, I translate it into software. I encourage you to start doing the same. In our world, automation equals software. As we saw with authentication, authorization methods have been getting more refined. Predetermined RBAC, role-based access control, is being supplemented with attribute, behavior, and context. If an authenticated user accesses a resource twice in 5 minutes from widely separate locations, that's a flag. If I'm logged in as me and try to access a resource 50 times in a second, that's another red flag. MAC and DAC are mandatory and discretionary access control. Mandatory is less convenient but more secure. It's imposed by the system or administrator and can't be changed by the user. Discretionary is the opposite. If you think about modern computers, our systems use both MAC and DAC. OAuth is open authorization, a standard protocol that allows users to grant third-party applications access to their resources by replacing passwords and other logins with tokens and trust relationships. Accounting is a means of measuring activity, and auditing is the verification of what actually happened, which allows us to observe in an unbiased manner. Auditing is mainly used for forensics, whether diagnostic, that would be us, or post-incident, that would be cybersecurity, and us. To a programmer, auditing means logging. Logs, of course, take resources to create, store, and review. Logging is often defaulted to low levels, so our code needs to help a system operator configure the correct level based on system criticality. Criticality speaks, again, to the value of information. Look for requirements of what to log and how long to retain it, though they may not be detailed enough and require our questions, interpretation, and refinement. Logs need to be stored at a higher privilege level than the application, and they must be immutable. There are separate logs for every significant resource on the network, say a database or web server or mass storage, or security relevant activity such as DNS lookup, login, privilege changes, etc. Part of your software design needs to make sure logging is available, and another part should consider what to do if it's not available. If you don't have any log retention requirements, you need to get some. Non-repudiation means knowing who did a thing. You can think of it as a combination of authentication, authorization, and auditing. Properly implemented, configured, and used, they all provide non-repudiation. Security requirements must specify the subjects, objects, and events for which non-repudiation is desired. Logs need to have evidence of who, what, where, and when, as well as what your software did in regards to those, plus hash values and certificate identifiers where applicable. Your logs, taken together, need to provide sufficient audit trails to detect disallowed activity. They must be tamper-resistant and tamper-evident. Renew your signature and certificate caches frequently enough, given the value of the resources your user is accessing. Buckle up. I'm going to spend a lot of time here because this is on us. It's our turf. Only you can avoid writing weak code. A weakness is a bona fide defect in the code. There's something wrong with the code. Thinking back to question 1 of our quiz, you did it. Weaknesses often don't change the functionality of the software under normal conditions. A given weakness may even present a known security risk, but that risk can be mitigated by non-software measures. Locked doors, armed guards, lasers, motion detectors, all the spy movie stuff. If the risk is known and not fixed or mitigated, by definition, the risk presented by the weakness is acceptable. But the decision to leave a known weakness unfixed isn't yours to make. Try not to create one. Try to fix it if you do. But if you can't, document it in your code and your workflow system. Let your boss, your lead, your customer, maybe your users know so that they can decide what to do about it. Our goal should be to tease out all the weaknesses in our software so that we can all mitigate them as appropriate. If we don't know about a weakness, we can't analyze it or mitigate the risk. Then it becomes a potential zero-day vulnerability, a weakness that no one knows about. The more you know about the common weakness enumeration, the more secure, the better your software will be. The CWE Top 25 forms the basis for most other Top X lists like OWASP and SANS. It's pretty stable year over year, the same weaknesses still appearing, largely because we programmers don't do security. Most of the enumerated weaknesses are failures to provide good enough CIA AAA, the concepts we've already looked at. Oversights that drive the rest are less than bulletproof exception handling and/or failure to provide security by default in the software configuration. Exception handling is a major cause of uncertain behavior in a system that attackers love to exploit. This is an area where incomplete requirements raise havoc. Returning to the operating system is not a useful solution. That's giving the attacker exactly what they want. At the process level, we avoid weaknesses by trying to follow the Secure Software Development Framework as described in the U.S. National Institute of Standards Special Publication 800-218. That's an awesome document, less than 30 pages long, that tells an organization what they should do to develop secure software. A big part of that framework is training people, like we're doing now. At the design and architecture level, we should be using and producing SBOMs, software bills of materials, and reviewing our design models with security experts together. SBOM tells a software user, which includes us as developers using third-party components in our code, what software they're using and who wrote it. If we all had been doing SBOM for the last 50 years, the cybersecurity landscape today would be completely different. But since we haven't, it's a very heavy lift to integrate them into the worldwide software supply chain. There are yet to be discovered tribes in the Amazon and New Guinea jungles who are trying to make SBOM happen. It's a species-wide effort involving lots of governments. SAST and DAST are static and dynamic application security testing, code scanners, and testing tools. You should be using them. DAST can include fuzzing, which can and should be done at any level of your code and system. Fuzzing or fuzz testing is feeding your code garbage, sometimes carefully controlled, carefully crafted garbage, to verify its resilience. It should be built into your DevSecOps pipelines, if any. Thinking about security, try to make your software configurable enough so that when a new weakness is discovered, the user or their security people can put a mitigation in place while you're working to create and release a patch. Remember, whenever you reuse someone else's code in yours, you own their weaknesses. If the weakness that you created is not completely mitigated and is reachable by an attacker, it's a vulnerability. This can get tricky because a mitigation step put in place earlier may change during the lifecycle, thus exposing a latent weakness. If a new vulnerability report reaches your desk, it's likely your highest priority. We need to understand the blast radius ASAP and fix the problem as quickly as, not as possible, but as appropriate given the risk. This includes all the affected deployed versions of the software, so hopefully you have a way of keeping track of them, or at least notifying your users. Since a weakness is a bug, right, your standard defect analysis and remediation process applies. You need to reproduce the vulnerability and assess the difficulty of the fix, and then fix it. The fast, quick, and dirty version of your lifecycle may apply depending on the criticality of the vulnerability. This is where DevSecOps with trustworthy continuous integration and delivery is extremely helpful. Once your fix has been deployed, you need to be ready for potential complications. Software is never done, and the lifecycle is a cycle. You may need to submit an entry to the CVE, Common Vulnerability Exposure Database, including a severity score under the CVSS, Common Vulnerability Scoring System. Vulnerability scores are much more complicated than weakness scores because they're context dependent. Scores might be different for each use case and deployed configuration. The measures listed on the slide are things that we should be doing both pre-release and continuously to detect and prevent weaknesses and vulnerabilities. When people started talking about negative testing in the aughts, I was confused. When someone finally explained it to me, I said, "Oh, you mean testing?" I don't understand the value of the distinction. You know your code, so you know how to do white box testing to best effect to try to break it. If your code is really resilient, you might need to cheat with defect injection to get it to fail. That should be our goal. I want us to understand the failure modes of all the software we write and maintain. Listed at the bottom are prominent examples of vulnerabilities that came from requirements, architecture, or design, the phases of the lifecycle that we programmers affect most for your Googling pleasure. Start thinking like an attacker. Seriously, you have my permission to look into hacking. Practice it if you want, but only on your own IT, and be very careful. Sandboxes, virtual machines, etc. We all need to become familiar with the attack framework. It gives us known attacker TTPs, tactics, the attacker's goal, techniques, how they attack, and procedures, examples of use in the real world. The KPEC is another very valuable resource for us programmers because it describes how an attacker can move through the system once they gain access. Thinking like an attacker, we should produce misuse and abuse cases for our parts of the system. These are just like use cases, but from the negative side. A misuse case looks at the damage a user might create, and an abuse case is what an attacker does. Creating these is a great way to start thinking like an attacker. Now, you can create abuse cases until the sun burns out, but a 1-to-1 ratio with use cases is a great start. Every use case should have an abuse case. Our system and software needs to be instrumented well enough with real-time and post-processed monitoring to be able to detect attacks with detailed logs and bulletproof exception handling. By the way, a favorite tactic of supply chain attackers at time of recording is disabling exception handling. We saw this in the recent XZ library hack that was fortunately detected and prevented before release. An exploit, a successful attack leveraging a vulnerability in software, is everyone's worst day. All the measures I've talked about, combined with all the hard ongoing work of our security colleagues, have failed. You may find yourself part of the organization's incident response team. Congratulations. You all need to work together to create a fix and publish a patch. In addition to what I've already talked about, we can make sure we've designed an efficient patching process. You need to think about the update and patching process early and throughout the development of your software or system. If you don't already have a trusted automated DevSecOps continuous build and release process, you should make your build process as trusted, secure, and automated as you reasonably can. We can think about the configurability of our system and proactively provide configuration options to tweak the balance between security and convenience and make sure that the default configuration is secure. We'll need to do an after-action review, understand the root cause, and adjust as necessary to prevent similar vulnerabilities. All of this is captured in the SSDF, by the way. Perfect software doesn't exist. So while we leverage highly trusted components for security functions, we need to be prepared to update them when they've failed and been fixed. Instead of installing and using the whole third-party framework, try to incorporate and use just the part you need. Keep it simple, stupid. But outsource what you can, minimizing your attack surface and sensitive data exposure, assuming you have trusted providers and strong enough service level agreements. Deploying infrastructure as code to bare metal provides numerous advantages to security. We can control every opcode operand pair executed by the processor. We have consistent, repeatable configurations and repeatable deployment. Security is therefore scalable. We reduce human error. assuming the automation/software in our processes is trustworthy. If we detect a compromise in our system, redeploying has a good chance of removing the attacker, although they can still hide in data, our development environment, or supply chain. And finally, disaster recovery and incident response are easier and quicker. Then there's insider threats. Insider threats are difficult. We don't want to think bad things about our colleagues, but realize that insiders can be merely clumsy or ignorant. The malevolent ones are usually much more damaging, though. All the usual processes that produce high-quality, secure software make it harder for insiders to ruin our day. Don't slouch on peer reviews and rigorously control changes to the system configuration in both development and operational environments. I've already talked about design and code review, and training is what we're doing now. Programmers complain about secure coding standards. We love to complain. But I found that by the time I stopped coding for a living, I had incorporated 90% of the MISRA C standard into my coding and design style without actually knowing what it was. Those techniques helped to keep my code from coming back from testing with new bugs. Of course, security clearances, background investigations, and a capable personnel security team help make sure that only good people have access to the system and software. In 1974, 51 years ago, as of recording, two cybersecurity professionals wrote a paper for the IEEE that laid out many foundational principles of secure computer system design. I just lied to you. Did you catch it? Cybersecurity wasn't a thing until many years later. These guys weren't cybersecurity experts, they were computer scientists. Salzer and Schroeder were part of the worldwide team connecting remote computers together for the first time, and thinking about what can go wrong when you provide more than one person access to a computer and the data on it. Their paper is cited in all the cybersecurity training I've seen, and virtually none of the software training I've seen. No matter how well I know and have lived this history, it still flabbergasts me. I'm old enough to kind of remember 1974. Smoking was everywhere, phones had cords, calculators didn't exist, libraries were 99% paper with a little bit of microfilm. TCP/IP was standardized in 1974 after this paper's writing. The ARPANET, which grew into the internet, connected about 50 computers worldwide. A network at that time was a terminal connected to the mainframe, usually in the same building. Here are their principles. I know it's a big eye chart. Pause and digest. You'll see that I've already discussed some of them. We'll dive a little deeper in upcoming slides. By the way, the protection of information in computer systems is perfectly applicable today. These principles are timeless. But the second half of the paper is about an archaic approach to database design and implementation. If you get the paper and read it, you can skip that part. Economy of mechanism. I still remember it well. The second lesson in computer science that I received. Keep it simple, stupid. The first lesson was that perfect software doesn't exist. Higher complexity usually results in less security due to lack of understanding and more attack vectors. Root cause analysis, especially for potential security issues, is much more difficult in a complex system than a simpler one. Rule of thumb: eliminate all non-essential services and protocols. Fail-safe defaults is kind of a meta principle. All these other principles, and your system from top to bottom, front to back, left to right, inside out, should be implemented in a safe and secure default configuration. Complete mediation. Assume an attacker is calling the code you're writing today. Sanitize and sanity check all inputs and expire your cached authentication tokens and session configuration artifacts appropriately. If you do this, authorization shouldn't be circumvented, even with persistent access and repeated attempts. Open design. Kirchhoff's principle is that a crypto system's security should be based on the secrecy of its key, not the secrecy of its algorithm or design. Assume your source code has been stolen, and make your software so secure that it doesn't matter what an attacker does. Separation of duties. No single individual should be able to abuse the system. This is why we peer review our code. It's why we have process gates in DevSecOps, and why only a few programmers can access the build system itself, usually with someone looking over their shoulder. Least privilege. If a user may require different levels of security for different tasks, it's better to switch security levels for specific tasks than to run all the time at that higher privilege level. Least common mechanism prevents inadvertent sharing of information by using separate processes when possible. This is the one that made me think hardest when I learned these, long after I stopped coding for a living. It's about avoiding single points of failure and providing different mechanisms for users at different privilege levels. That way your administrator doesn't accidentally break something when they forget they're logged in as a privileged user. An overlap of security with human factors is to make sure your UIs don't look similar for substantially different functions. Self-destruct and run built-in test should look and feel very different. Speaking of human factors, we have psychological acceptability. Don't ask me how I know, but there's a sign in a nearby maximum security prison that reads, "Security is never convenient." It's true, of course. Onerous password policies result in passwords being reused and or written down. Of course, none of us do that. Make doing the right thing easy for your user, and make it harder for your user to make an error. It's not just nice, it's a security principle. CAPTCHA means completely automated public Turing test to tell computers and humans apart. Work factor is another meta principle. Rear Admiral Grace Hopper, one of the OGs of computer science, posed a rhetorical question in a lecture long ago. How much security do you need? Well, how valuable is your data? Secure your software using these other principles concordant with the value of the information in it to an attacker. Some attackers are make that infinitely determined. So this principle is less applicable to us nowadays. But even if your code is far from the most sensitive or dangerous parts of the system, practice defense in depth. Compromise recording is one that catches many programmers by surprise because we don't think about security, and it doesn't occur to us that our call stack or other internal data could be hugely useful for an attacker. I talked about logging and monitoring earlier, but in the meantime, SIEM is Security Information and Event Management, a way to make useful forensic information available during incident response. There are a few more concepts that were developed after 1974 that I want to talk a little bit more about. Reuse of trusted components, we saw this earlier, is great because it increases both efficiency and security. But it's bad because we usually don't know the code well enough and it produces a monoculture environment, so failures have a larger blast radius. Resiliency has a large body of work, and many of the techniques I listed earlier under availability are also resiliency measures. NIST Special Publication 800-160 and the ISO 27001 standard are two Bibles of resiliency engineering. Finally, defense in depth is another meta control, applying all the other principles everywhere. Remember in Lord of the Rings, the Two Towers, where Saruman's orcs just needed to penetrate Helm's Deep's outer wall and they ran amok in the interior? It's like that. Perimeter security isn't enough. Again, realize that an attacker could be on the other side of that interface. In conclusion, look at all the information you're processing and assess it for value to you, users, and attackers and do your software development thing accordingly. The MITRE resources are listed in priority and applicability to our day-to-day work. At least read the Getting Started or FAQ pages for each one. CWE, Common Weakness Enumeration, is a list of bona fide defects from all phases of the life cycle. For example, CWE 1008 is the parent weakness for architectural concepts. CAPEC, the Common Attack Pattern Enumeration and Classification, describes how an attacker can move through a system. It's great guidance for defense in depth. Attack is indispensable for learning to think like an attacker. The CVE, Common Vulnerability Exposure, is a massive collection of identified vulnerabilities. When a weakness is exploited, there can be a different vulnerability for each version, hardware configuration, operational use case, installed configuration, etc. Defend is a resource mainly for defenders of the network, our cybersecurity colleagues. Speaking of them, make a cyber friend. Just as we don't know how they do their job, they don't know how we do ours. We know things about the system that they don't, and vice versa. Find someone you can ask stupid questions to, and then they can ask you stupid questions. They don't have to be high level or experienced. We just need to start working together more. So I promised you an answer earlier. Having thought primarily of security for years, I've realized that the only truly risk-free software is what you're not running. The decision to automate the processing of information involves accepting some level of risk. If you can think of software with no security considerations, I'll be happy to hear about it and discuss. But don't forget about integrity and availability.